off looking at the electrical driving force, and we were talking about the factors that determine that force, and then we moved on to look at the magnitude, excuse me, the magnitude of the electrical driving force. So we know the electrical driving force is based on the charge on the particle, whether it's a positive cation or a negative anion. We also know that it's based on the polarity of the cell or the state of the cell, whether there's an abundance of positive charge on the inside or negative charge on the inside and vice versa on the outside. So those two things determine the type of electrical driving force, whether it's positive or negative. Let's look at what determines the amount, the magnitude, or the strength of the electrical driving force. So the magnitude of the driving force is basically determined by the strength of the membrane potential, okay, the strength of the membrane potential. And just to describe this a little bit more, we talked about the membrane potential being the separation of charge. So the degree of that separation of charge, how much of a difference exists between the inside and the outside of the cell will determine the actual strength of the membrane potential. The other thing that determines the magnitude is the amount and type of charge. The amount and the type of charge. On the particle in question. Okay. And that means whether it's a cation or anion, so cation versus anion, that's the type of charge, or whether it is monovalent. Monovalent versus being divalent. And the example is if it has one charge versus two charge. Right? So one charge versus two charges. Okay. So depending on the type of charge and the amount of charge, that too will determine the strength of the electrical driving force, or the strength with which that particle wants to move to get to the opposite side or the opposite state of the cell. So let's look at an example to drive this point home. So here's our first hypothetical cell, our second hypothetical cell, and then a third scenario over here. Let's start with the first one and think about our cation sodium. So if we have positive charge outside, negative charge inside, okay? And we know that sodium is positively charged. Sodium, the electrical driving force acting on sodium, wants to move sodium into the cell. The strength with which sodium would move, we're going to put this as, right, which is the strength of the membrane potential here. So our membrane potential V subscript M is going to be equal to negative 60 millivolts. So what that means is that in this scenario, there is negative 60 more negative charge inside the cell than the environment outside the cell, which has an abundance of positive charge. So our membrane potential is -60, and this is the strength with which sodium wants to move to the inside of the cell. Let's look at two other scenarios to look at how the strength or magnitude can change. So now we have even more positive charge, right? We have twice the amount of positive charge outside the cell, twice the amount of negative charge inside the cell, okay? And our membrane potential in this scenario is going to be exactly double. So our membrane potential is now -120, okay? So what does that mean? The strength with which sodium wants to move is now going to be twice as much. Now sodium really wants to get into the cell, and we have increased the strength of the membrane or the electrical driving force acting on sodium. So as the strength of the membrane potential gets bigger, as the amount of negative charge inside the cell gets more, positively charged ions want to get into the cell even more. The proportion of the electrical driving force acting on the particle is going to be just as great as the strength of the membrane potential. Let's look at a third scenario. So now let's think about our original cell here, where we have positive charge outside the cell, negative charge inside the cell. So pretty much the same as what we saw with our first scenario up here. But now if we consider a divalent cation like calcium, so here's calcium, and because calcium has two charges, the strength of the electrical driving force is going to be just as strong, right? The membrane potential here is also going to be just as strong because calcium really wants to get into the cell, and because calcium has two charges instead of one. So it's going to be a similar electrical driving force and a similar membrane potential. So our membrane potential here is also going to be -120 because we have a divalent ion instead of monovalent. Okay, so that is to say that the magnitude of the electrical driving force, the force that is trying to move our particles, is going to be following the type and amount of charge as well as the state of the cell. So both of those factors play a part in the strength or magnitude of the electrical driving force. Chat box is blocked up, but let's see. Okay. Any questions at all, please just drop them in the chat box. Okay. And I'm going to go ahead and do this and let's keep going. So now we can begin to think about combining those two separate forces. The chemical driving force, which is based on the concentration gradient of the particle, where there's a high concentration on the inside, a lower concentration outside, and so the particles want to move from the inside to the outside. Okay, I'm getting a question here in the chat. How did I determine the membrane potential on the examples, and why was the last one -120? So good question. The last one was -120 because we had a divalent cation. Remember, the membrane potential is due to the separation of charge. So if we're thinking about a scenario where there's more negative charge inside the cell, more positive charge outside the cell, and we have a greater separation, a greater degree of difference in those charges, then we're going to have a stronger membrane potential. If we also have anions or cations that are carrying more charges, So if we look at calcium, calcium is divalent. So that is going to create a greater separation of charge as well. And an ion like calcium trying to get into the cell is going to really want to get in, but also the state of the cell separating the inside, which is negative, from the outside, where there's an abundance of divalent cations will create a stronger membrane potential, as well. Okay, so we want to think about two things. We want to think about the type and charge on the particle, as well as the state of the cell, right? The separation of charge and what degree there is separation of charge. Okay. All right, and we'll look at a few examples to help kind of clarify this as we go along. This is also going to come back when we look at the establishing the resting membrane potential. So I'm going to kind of go a bit slower here, just so that when we get to chapter 7 and we review this, it makes a bit more sense. We're going to need to understand this to understand how neurons behave and how they can fire the action potential. So when we think about combining those two forces, so chemical driving force is based on concentration gradient. A positively charged ion like potassium would want to move down its concentration gradient from high to low. But if we think about the electrical driving force acting on potassium, it's going to want to move potassium to the inside of the cell. All right. And so if we think about this scenario, the chemical driving force and the electrical driving force are happening in equal and opposite directions. So the particle is not going to move. This is what we call the equilibrium potential. When the membrane potential is at -94, because this is the specific equilibrium potential for potassium. So this is a fixed number for each ion. Potassium has its own equilibrium potential. Sodium has its own equilibrium potential. Calcium will have its own. For potassium, it's -94. So when the membrane potential gets to that value as well, when those two numbers are matching, the forces are in equal and in opposite directions, and there's zero movement of the ions in question. All right. So when we think about a particle in general, it's really moving to obey both of these forces. So we want to think about which of the force is stronger, which is greater, and that's going to be the direction that that particle wants to move in. But if it happens to be at equilibrium, then both of those forces are canceling each other out, and the particle will not move at all, right? So that's something to bear in mind when you think about the membrane potential, and then now thinking about the equilibrium potential of each of our charged particles. So let's kind of describe that a bit more. So if the chemical and electrical forces are acting in the same direction, this is pretty straightforward. We simply sum those two forces. We find the magnitude, which is the number, the numerical value of each of those forces individually, and we simply combine them in order to identify the electrochemical driving force. Now, the magnitude of that is going to be adding those two numbers together, and the direction of that is going to be which force is stronger. So if the electrical driving force is stronger, the particle is going to move overall in that direction. And we're simply going to combine, those two forces together. If the chemical and electrical forces are acting in opposite directions, so this is where things get a little bit more complicated. Now we're going to try to find the stronger force, and that will be the direction of movement. Okay, so let me just reiterate that and repeat that. If the forces are in the same direction, we simply combine them, and that direction is the movement of the particle. If the forces are in opposite direction, we find the larger force, we subtract the smaller force, and then the direction of the larger force is the direction of movement of the particle. And this is going to be a smaller magnitude of movement because we had to subtract the smaller force. So it's going to be the larger force subtract the weaker force in the overall direction of the stronger force. So this brings up a question. If a chemical gradient existed, under which conditions would a particle not be transported across a membrane, even if the membrane is permeable to that particle. And we kind of just discussed this, but think about what condition would have to exist. If a chemical gradient existed, what condition would have to exist for there to be no movement of the particle, even if the membrane is permeable to that particle? Any thoughts about this? So if we had a chemical gradient, which means we have a chemical driving force, what would the electrical driving force have to look like in order for there to be no movement of the particle? Okay, perfect. Yes, I'm seeing a few responses here. It would have to be equal and opposite. So the electrical force would have to be equal to in terms of the magnitude and opposite in terms of the direction. Perfect. Okay, so that is absolutely correct. We'd have to have an electrical force that is equal to in terms of the strength, but opposite in terms of the direction of the chemical force in order for that particle to now be at equilibrium and there will be no movement. Okay. So let's talk a little bit more about the equilibrium potential. And this can be a bit of an abstract concept to kind of grasp. So let's really break it down. So the equilibrium potential is a type of membrane potential. So it is the specific membrane potential that exists when the electrical and chemical driving forces are in opposition. Okay. As I mentioned earlier, it is specific for every single ion. So if I tell you that the equilibrium potential for potassium is negative 94, that means that when the membrane potential gets to negative 94, potassium is at equilibrium. So the chemical force and the electrical force acting on potassium are canceling each other out. So this is going to be in opposite directions and the exact same magnitude at that specific membrane potential. We'll look at an example for sodium later on. Sodium has an equilibrium potential of positive 130. So when the membrane potential is at negative 94, potassium's not moving, but sodium is moving because sodium is not at equilibrium. When the membrane potential becomes 130 or 130 positive, then sodium will be at equilibrium and there will be no movement of sodium at that membrane potential. So it is the membrane potential that exists when the forces acting on a particle are equal and opposite, and there's no movement of that particle. Okay. So if the membrane potential is equal to the equilibrium potential, the force of movement is zero. All right, so again, thinking about the exact same example here, the way that we represent the equilibrium potential is going to be E subscript the ion in question. So E subscript K here for potassium. And again, that value for potassium is negative 94.